Hey, I'm Sam Bateman with the Autonomous Robotics and Perception Group at CU Boulder, and today I'm going to present our paper, Better Together, Online Probabilistic Change Detection in 3D Landmark-Based Maps. So, at this point, most people in the robotics community are aware of simultaneous localization and mapping, known commonly as SLAM. More specifically, a modern and common form of SLAM is known as factor graph-based SLAM, which encodes relative measurements between poses and sometimes landmarks into a Bayes graph and optimizes the parameters of the underlying distribution subject to the cost function which is implied by said Bayes graph. Through this joint optimization of parameters, one can build up a maximum likelihood estimate to the map of an environment, as well as the robot's localization relative to said environment. A small example is shown on this slide, where edges in the factor graph are measurements which are codified in something like a constraint called a factor, and nodes, which contain the parameters, are shown with blue rectangles for robot poses and blue circles for observed landmarks. For this presentation, we will address a major failure mode in the previously described sparse landmark-based factor graph SLAM. An important note is that all observed landmarks are assumed to be static, so the only cause for movement can be assumed to be the movement to the sensors and therefore the robot through the environment. Otherwise, there would be a chicken and egg problem of whether the world is moving around the robot or the robot is moving through the world. This is a core postulate in the formulation of the SLAM problem, which is well known as the static world assumption. However, in the environments we wish to operate our robots in, we can rarely, if ever, make this assumption. Take, for example, the simple diagram on screen, where a couple of landmarks are on vehicles. When our robot revisits the location at a later time, assuming the previous map is invariant, one of the landmarks is occluded by a parked car and the other two have moved and parked again. The majority of visible landmarks emit measurements which conflict with the robot's own estimate, leading to optimize to an estimate which conflicts the least with all the measurements made, leading it to estimate it's in the center of the road in this case. The result in this toilet example is that the car crashes into the parked car while trying to center itself in the lane. While this is obviously a specific example, this represents a serious failure mode of SLAM rising from the challenges posed by lifelong operation in a single map, where upon returning to an area, landmarks have moved or are occluded due to dynamics in the environment. As the scale and scope of robot operations grows, these problematic occurrences happen with higher and higher frequency, rendering the current formulation of SLAM ill-posed for lifelong operation in dynamic environments. Many people have attempted to solve this problem in the past, where the majority of approaches fall into either of these two categories. One way of solving these problems is separating the map into dynamic and static portions and then reducing back to a static SLAM problem, such as in Dennis Wolf 2005. However, there are some problems with this approach. Some labeled dynamic portions of map may be static for a period of observation and contain the most salient landmarks and features to constrain trajectory over a short time horizon, such as parked cars on the side of a road in a busy street. Conversely, some labeled static portions of the map may change over lifelong deployments due to, for example, construction in the context of autonomous vehicles or movement of furniture in a human dwelling. Another proposed solution is that of the multiple map hypothesis, such as in Timothy Morris's 2014 paper on the subject. Again, there's a problem. Storing and maintaining multiple hypotheses is very expensive, both computationally and in memory, making it difficult to use in long deployments. Each of these maps will accrue different changes in error over time, making each map worse over time. A different approach was suggested by Rosen in his 2016 ICRA paper. What if, instead of assuming a static world, we assumed a dynamic world, which is to say we assumed all landmarks were semi-static, where all landmarks eventually move or cease to persist in the environment. Instead of a binary dynamic or static classification, the difference between landmarks would be the time period before which a semi-static landmark becomes dynamic, so to speak. This period of non-dynamic behavior is referred to as the survival time of the object in this work, reaching into the field of survival analysis to base the discussion. The idea behind the independent feature filter is that one can use a Bayesian filter per landmark to estimate the persistence probability of that landmark in the environment based on the observations at each possible observation time step and some prior on landmark survival time. If the persistence probability drops below a certain level, the associated landmark and connected factors will be removed from the factor graph, effectively cleaning up missing nodes and factors which would otherwise grow the map proportional to the deployment length. For a visual example of this strategy, let's imagine that our robot is returning to the area we had mapped before. The measurement of landmark 1 is easily and correctly rejected as the vehicle is moved from its previous position. This landmark would be removed from the map and a new landmark would be introduced at its new position with none of the prior constraints relating to the old position, maintaining consistency of the factor graph and the real world over time. However, there are problems with this. An obvious one is shown in this slide. Landmark 2 is occluded and therefore will be dropped from the map by the independent feature filter because it's expected to be observed and isn't. This means that any occluded parts of the map, a common occurrence in 3D dynamic environments, will have all their constraints removed after each occlusion, resulting in a large loss of information and inefficient graph operations, hindering real-time performance and high accuracy. Look at the math really quick. We see this filter is just an application of Bayes' theorem, where tk is set to be the survival time of the kth landmark, or the time when the landmark ceases to persist statically in the environment. The jk represents the observations of the kth landmark from the first to the nth possibly observable time step. From this model, the likelihood is expressed as the product likelihood of the probability of the observation of the landmark at each time step. The prior is simply a provided survival function engineered ahead of time, and the evidence term is built from the likelihood with a clever observation about the integral composing it. Despite the problems we just highlighted about this approach, there's a lot to like here. For one, the provided iterative update is very computationally efficient, and the formulation is quite simple relative to the complexity of the process it's trying to model. An interesting attempt to address the problems of the independent feature filter is the joint feature filter by Nobre in their 2018 ICRA paper, where they formulate a feature filter which is based on using the nearest neighbor persistence probability to estimate the pairwise conditional persistence probability of each of these neighbors to infer change detection of features which may not yet be observable. They make an interesting observation through this. Landmarks which are locally close observe similar behavior with regards to persistence. Unfortunately, this formulation increases the complexity of the problem by a lot. The simplifications made in the joint feature filter to make the problem they propose feasible involves utilizing the persistence process of a single random observed landmark to be summative of an entire group of landmarks, resulting in large amounts of instability over time and poor performance in complex dynamic 3D environments. What would really be desirable is something that retains the simplicity and stability of the original independent feature filter from rosin, but doesn't suffer from the problems of occlusion, and can take advantage of the correlation between features as proposed by Nobre. So think of this. What if you were barking up the wrong tree by trying to estimate landmark persistence, which is a very challenging stochastic process to model due to the fact that so many factors influence its observability? Instead, think of how nearly every autonomous system deployed today is already tracking semantic objects and will soon be performing instance segmentation and panoptic segmentation online, given the recent research in the area. It seems likely that we could propose collections of landmarks as we observe them which lie on a single object, where this collection makes a clique of landmark nodes in the factor graph. Because these probably lie on a single physical object, if we estimate the persistence of the clique rather than the persistence of an individual landmark, we can assume that the component landmarks continue to persist as long as the clique does. So what does this look like intuitively? Here we display the cliques as ovals around collections of landmarks which are on a single object. Like the independent feature filter, we correctly remove landmark 1 with this strategy, but we can also remove landmark 11, even though it's not within our sensor model to be able to observe it. This is because we know these landmarks are in the same clique, and we assume they share persistence because of this. Thus, because our filter detected that landmark 1 no longer persists in the same place as before, and there's no evidence that this clique still persists in the same location, the filter can remove the resident nodes in the clique and their connected factors from the factor graph. In addition, even though we expect to see landmark 2, and we don't due to the occlusion by the other vehicle, because we consistently observe landmark 8, it would be unlikely that the clique of landmarks 8 and 2 no longer persists. Thus, we retain landmark 2 despite never observing it. Obviously, as real landmarks are much more plentiful than this due to the features generally used for this application, these cliques would be populated with many more landmarks to help reject false positive detections and misdetections. So what does this construction look like mathematically? Well, first we make the assumption that at a given time step, observation of all features which are expected to be observed in our sensor model are conditionally independent of one another, or it is conditioned on the persistence of the clique. The intuition behind this is that without any other information about two landmarks in a clique other than them being in the same clique, we can't assume that their observability is correlated, as one could be occluded and the other not, or one could have a visibility range which is different than the other, and this could be varying with time. Maybe one could model this, but we'll leave that for future work. With this assumption, we can formulate the likelihood simply as the conditional product likelihood of all observations of landmarks in a clique at a given time step given persistence of the clique. We can then easily reformulate the independent feature filter to estimate joint clique persistence rather than the individual feature persistence. First by swapping out the likelihoods, then going through a similar derivation of the evidence with the new likelihood term and the assumptions we just made, and trading the landmark persistence prior term with a clique persistence prior. A major and easy to miss implication is that because cliques will often be tied together by some semantic grouping provided by some external algorithm, one need not engineer a landmark-specific prior, which is quite hard, because the landmarks cease to persist for a variety of complex reasons. Instead, one can engineer or design a prior over a semantic class, which is far easier to reason about cognitively and far easier to extract data from existing systems and observations. To evaluate our methods, we pitted it against the methods described in Nobre 2018 and Rosin 2016 in a simulation where a simulated sensor, either a camera or a LiDAR, was moved along an arbitrary periodic trajectory that passed by a collection of cliques that have some persistent survival time. We evaluated the accuracy and efficiency of the filters over this domain in 1,000 simulations and present these results in depth in our paper. However, for a short summary of these results, we find that our method outperforms the independent feature filter and the joint feature filter on the LiDAR sensor domain and performs competitively or better in the camera sensor domain against both methods. The reason for the discrepancy in the case of the camera sensing modality is because our partial observability model and sensor degradation model, which is described in detail in our paper, utilize distance of a landmark from the sensor as the sufficient statistic and don't incorporate the field of view of the camera, where objects are physically close, which may leave the visual frame quickly, but we would expect that they would be high probability because they're very close to the sensor. On the right, we can see an example rollout of our simulator, comparing our joint clique filter with range-based sensor degradation, which is shown in gold, compared against the independent feature filter from Rosin 2016, which is shown in blue. These which shows the estimated persistence probability over a series of passes by a clique using a camera sensor model. The red vertical line shows the true survival time of the clique. The periodic decreasing value is the prior taking over the estimate in absence of observations between clique observability. We can see that the joint estimation of persistence probability of our joint clique filter, which utilizes observations of all component landmarks in a clique, rather than just one, is made much more resilient to misdetections than the independent feature filter, resulting in a more stable, more reliable filter due to these changes. To close, I'd like to thank my co-authors, Kyle Harlow and Christopher Heckman, and the funding sources which helped make this happen. Thank you.